Hello everyone, you're welcome to another video session of Python for All, Py4a. In this video, I want to give further examples on while loops. I'm doing this video so as to use these examples to show how we can effectively use the while loop. And so we will start by looking at the Newton's method. We'll talk about, give a background to the Newton's method, and thereafter would build the algorithm, write the code, and then run the code to see the results from uh, the Newton's method that we're looking at. So first, to lay a background, what is Newton's method? It is also known as the Newton-Raphson method. It's a recursive algorithm for approximating the roots of a differentiable function. So first, let f of x be a differentiable function. Okay, select a point x naught, which is an initial approximation to the root. So we make a guess, okay, as the initial approximation to the root. Then calculate the approximate root recursively using this expression where the next value of x is equal to xn minus the function at xn divided by the derivative of the function at xn. We can rewrite this expression as, in this case, so that I'll be able to write the recursive function we as xn, so that each time we are recursively looking for the value of xn and replacing xn, it will become xn minus 1. So in other words, what we are simply doing here is to replace n with n minus 1. So if you put in n minus 1 here, it becomes n minus 1 plus 1, which is xn. If you put in n minus 1 here, it becomes xn minus 1 minus. If you put in x minus 1 in n, it replaces as f of x n minus 1. And so also the derivative, it becomes f prime of x n minus 1. So in other words, replace substitute in place of n minus 1 in this first mathematical expression. It gives you the second mathematical expression where x naught is given. And so, and then f of x naught is approximately 0. That's what we want to do. We want to ensure the function of the root is almost 0 or gives us 0. Once we achieve or attain this condition, it means that we found the root to that function, and that value that makes the function approach 0 or approximately 0 is the root of the function. So, but then we were given that a condition that the function here is less than epsilon. Epsilon is a small value. So to do that, we will look at write the function this way. Let me mention here that this mathematical expression here is a recursive form of the initial or the first expression. So we define the function Newton. It takes f, a callable function takes x here. X is the initial value, but because we want to call this, rewrite this value of x while we iterate, we just define it as x. Then the next is df dx, which is the first derivative. It's a callable function. Then epsilon, which is a small value. Okay, and then the maximum number of iteration we don't want to continue to iterate infinitely, so maximum iteration is 100. So what happens if the number of iteration hits 100 and we're yet to find the root? The iteration simply stops, or it becomes the program exits. So we put in our docstring. This computes the approximate root of the the root using Newton-Raphson method. So here we have arguments, callable function, callable derivative of function. X is a float, which is the initial approximate root. Max iteration is an integer, maximum iteration default is 100. Then it returns the approximate root. So let's start writing. So here, first of all, to use a while loop, we have to initialize n. So when n is 0, n is equal to 0, so that for every iteration we increment n until we get to the maximum iteration. So while the absolute of the f of x is greater than epsilon, remember here we said that the condition is that the function of x must be less than epsilon. That's the condition to be met. So to be able to meet this condition, we need to reverse it here. So here it's while this is greater than this, keep doing something until it hits less than. So while this is greater than this, remember the while loop, we say the while loop runs until the condition is false. So now we need to make the condition here. This is this is the condition here. The condition here is true. So the false condition is the opposite of the true condition. So that's why we're using greater than. So while this is this greater than epsilon and n is less than or equal to, because n has to be, we want to hit the maximum iteration 100 and not go beyond it. So n, for it to be false, has to be less than or equal to the maximum iteration. Then what do we do? Then we call the recursive function, where we now say x is equal to x minus the function of x divided by df dx. And after that, we increment n by 1. And then the function returns x, n, and f of x. X is the root that returns the number of iteration and then the function of f of x. So to demonstrate this, we'll run this code. I'll run this code, then I have my function in my namespace. So next, let's use that to solve this example here. G of x, the function is x cubed minus 3x. So first, we need to differentiate this function. It gives us 2x minus 3. Then next, we need to obtain x for when g of x is equal to 0. So first, we code the function def g. It returns x squared minus 3x, and the derivative returns 2x minus 3. Okay, I haven't done that. Then we can now call, we remember the function returns three values. So it returns x, number of iteration, and the function of x, which I'll call f of x. Let me call it f of x. So in here now, we call the Newton's function and pass f equals to g. We have talked about this when we discuss function. It's always good to pass all the functions this way. Python recommends this rather than just passing the function as position argument. So even though it is defined as position argument, we can actually pass them as named arguments. So f is equal to g, x is equal to 2. So our initial estimated root is 2, and then the f dx is this. You can see that I only pass 3 inputs because the other two inputs have default values. So I just leave them at their default values. So once we've done that, the next we want to now print the roots, the number of iteration, and the function. And here should be f of x. So let's run this cell and let's see the result. If I run this cell, you see the root of that function is 3. And then how many iterations have I taken to arrive at that? 5. And the function, you can see this value is close to 0. Now let's look at another example here. We'll look at h of x equals x multiplied by exponential raised to power minus x squared. So let's first of all find the first derivative of this. It gives us this, and then obtain the value of x for h of x equals 0. So to do this now, we need to because of the exponential function, we need to import numpy, which is used for numerical computation. So we import numpy as np. So I define the function h of x equals x multiplied by numpy dot exponential. You can likewise use the math library import math, but I prefer to work with an array and vectorized array. If you work with the math library, you are working with scalar, scalar values. So I prefer array computation. So that's why I'm using NumPy. So next to derivative as well, you code in the derivative, write the expression. And this time around, let's call it f of x. So I'll return again, same, and I'll print out the values. So if I run this cell, let's see what we have. You see the root of the equation is 4.267 and but approximately 4.3. And how many iterations have I taken to arrive at this? 13 iterations, and you can see the f of x value, uh, almost zero. Now, this is, let's look at an improved Newton method or Newton-Raphson method. So to improve this method, what we'll simply do is to redefine this function again, same function, but this time around, because we want to reduce the number of times that we make a call to f of x. Here we call it for as long as, we call it so many times um, in this function. So here we just first of all assign an f value to f of x, then initialize n, saying n equals 0, and then we want to pass in a flag here. In other words, we can store the previous value of x and f value. If you notice in the first function, we didn't store the intermediate values because the value of x is overwritten. We only store the final value at the end of the iteration. So, but here we want to keep a memory of it. So, first of all, we pass in a flag store is false. That's the default argument. So here, if store, so if store is false, of course, don't do anything. But if store is true, that's where we use if condition here. If store is true, then store it in mem. And what do we store? We store a tuple of x and the function value. So we go again, same function, while absolute of this time around function value, but that's equals to f of x is greater than epsilon, and n is less than or equal to the maximum iteration. Then we also store the df dx value, which is the derivative, first derivative value. That becomes df dx of x. So now, since we have stored that, we put in another condition here and say if the absolute value of df dx is less than epsilon squared. In other words, it's less than very small. We want to see, because we have a condition here that, remember, in, let me go up a little bit, show you in my, yeah, here we said the function should be less than epsilon. So we want that value to be so small. So we'll put in that condition there. I multiply, instead of hand coding this, putting a very small value like 1 times 10 raised to the power minus 14, I simply just multiply the epsilon value by square the epsilon value, and this gives me, 1 times 10 raised to the power minus 14. So I want a very small value. So if it is true, if it's very small, then raise a value error. You don't worry about this. We will talk about error handling very soon. That you see the types of errors that we handle in Python: syntax error, value error, zero division error, input error. A lot of them, we're going to discuss them there, but I'm just using one of them here. So raise value error, and then passing my f string, Newton value, the derivative of f of x equals. So raise the value and print out the derivative of f of x for me, the of f of x. So we continue inside the body, outside the if condition statement, x equals x minus f value, df of the value, then increment n again because the while loop keeps running. We want to run it for until the maximum iteration. That's what we initialize. If we don't have that condition there to stop it, the stopping condition, it runs infinitely. So increment that, and what is increment that? Calculate a new value. You cannot assign a new value for f value, which is f of x. Then if store, of course, append the value of x, that those calculated intermediate value to our mem, okay, a storage container here, mem. Then outside that loop, the while loop, this is inside the while loop. Outside the while loop, we'll call again if store, return x and mem. In other words, if store, return the final value of x and those intermediate values of x and the function value. Else, if you are not storing, simply return the final value, the number of iteration, and f value. So these two conditions, we can space it here, This if condition statement is outside the while loop. So it's just an additional um, conditional statement to handle when you return the stored value or not. So let me run this to keep it again in my namespace. If I run this, it overwrites the first function, Newton function in my namespace. So this new Newton's function goes into my namespace. Now let's use this function, the last one we looked at, which is the h of x, this to demonstrate the example. So here we return the function, define h of x, then the h, the derivative. And so this time around, I want to return x and results. Results are the stored intermediate value. And I call here and say Newton, f is equal to h, x is 2, my guess, initial guess, the derivative is the h, this function. Mind you, notice I did not say f is equal to h of x. No, the function is callable. Okay, yeah, just passing the function directly you have defined. If the function is not defined inside this Moodle script or another Moodle script, simply import it into this Moodle script and pass it directly. It's callable. Python fully understands how to integrate and call the respective functions so long as they are defined and passed in correctly. Then here I say store is true. So because I've stored it, I want to print out. Remember, it stores a tuple value. So first of all, I print the roots equals x. Okay, and I use can see this formatting pattern here. I want to have the signed decimal value. Okay, whole number. Then I'll move to the next line and say for I in range length of results. Okay, fine. This is often the way you write this as a newbie. Okay, that's why I've written this. But normally I'll show you a modified way and the best way of writing it. Don't ever use range length. Okay, so but let's do that now. Print the iteration. Okay, print to three iteration incremented by one I plus one. You know, Python starts from zero, so I want to start from one, so I return it as I plus one. It can't prints out one instead of zero. And to okay to three with three digits, so I have three digits. Okay, three digits of it. So I want to print if it's one, it adds two zero. Okay, in front of one until it gets to 100 because 100 is three digits. So then again, that's what it prints. Then put a colon, print the function value. Now, since the result returns a tuple, so the a tuple, remember, is a list of tuple. So I'll first of all pick result of I. Okay, as is looping I, it will pick result of I, and the inside the I, okay, you're going to have different results, result of one, result of two, result of three, or five. Inside the first result I, for each time it looks through the range of that result, I should pick the first value, returns is x, so f of x, that's what I'm printing there. Pick the first value and um, write it to the signed decimal value equals the return value now of that f of x is pick the result of I again of the second value. Remember, Python indexing is zero. So first value of that tuple is zero. Second value of the tuple is one. So that's what I'm doing here. If I print it, you will see the result. So let's run this cell and see what we have. So come here, I'll run the cell. You see what we have. The root is 4.3. I've approximated it. Okay, I've given it this up to this just give it, you can see it shows how many decimal place, 1 2 3 4 5 6 6 decimal place, and then it tells me first iteration, that's the printing one instead of zero. I have said I plus one, so it prints zero. F of two, of course, the first initial guess point is 2, so it picks it I of 0 to the tuple and it returns the value of it, and then it goes to the next one, next one, next one. You can see the value now starts going, approaching 0 0 0 until the 14th iteration. So here you can see that I have 14 iteration to give me this result. That is how the modified Newtons work. Then again, I'll come here in this cell here. I simply have said instead of using for I in range of length of results, use the function enumerate. I'll talk about this enumerate function in my next three videos. They are valuable functions that we need to talk about in Python, how to use it. Very powerful. So I'll just say for I comma res, okay, or results. Instead of res, I can say results in enumerate of results, because I remember x and results I've called Newton. Here I've made a guess of one. Remember initially I made a guess of two. Here I guessed one. Let's see how long it will take when we make put in the initial guess as one, and then I want store to be true. So I'll print here. Let's change this also. This becomes results, and this becomes result. You can see if I've used, since I've used enumerate, I don't have to write result of I, result of I. The I here picks the position, and the result picks the value. So since I'm interested in the value, I don't want to index the value. This is more Pythonic and improves readability. Unlike this first case, okay, readability is being is affected here. So, but here is more readable. So I say for I in enumerate it. Sometimes in Python, since I don't use that position, the index for anything, we'll just use underscore for underscore comma result in this. Let's use I first and let's see the result. And I also turn it to underscore. You see the result, same result. So anytime you don't need the index and you're enumerating, you simply just underscore for it. It becomes overwriting. The advantage of that is that it's memory efficient, as the values of I are not stored, though they are simply overwritten. Let's run this and see the result that we have. Now I run this loop, you see, same result. You start with f of 1, and then f of 2, and go on and on. You can see that when I started with 1, and how many iterations do I have? It took more time. I had 14 iterations, though 15 minus 1, 14 iterations. So you see, in Newton's method has a disadvantage, and the disadvantage is that it largely depends on the initial value, the guess you have made. So if you guess far away from what the roots should be, you take more time. So it takes more time to iterate, but that's not what the essence of my video is. Also talk about the while. With this, we have come to the end of this video. If you have any question, please leave it in the comment section. Give this video a thumbs up, like this video, share this video, and if you are watching and have not subscribed to my channel, please do well to hit the subscription button and also the notification button to get notified of my new upload. Until then, I will see you in my next video. Bye.